So the last thing we talked about was how to add two vectors together. We started with this black one and this blue one. Now this blue one I think was over here somewhere, so I dragged it over to here. This red vector, the resultant vector, was the sum of this vector plus this vector. This is called the triangle method. Obvious reasons. Obvious reasons. There's another way to do this. It's essentially the same thing. Let's start over. I want you to draw vector CD and AB again. So here's vector CD. And then let's put vector AB over here. Try to make them the same direction and magnitude. The other way to add vectors in space is called the parallelogram method. It's essentially the same thing. So on your guys' magic paper, I want you to take the vector that you've drawn and drag it over to here on your magic paper. Can you do that?
Yeah.
Oh, you can't do that? But anyway, this time instead of putting the terminal side on the initial side like this, you're going to put both initial sides together like that. So just wherever you drew AB, redraw AB over here, the same direction, same magnitude. You following so far?
Yep.
Now what I want you to do, starting on the terminal point here, D, I want you to draw a dotted line that's the same length as vector AB and in the same direction as AB. So draw a dotted line. Try to do the same direction, same magnitude. That look about right? That looks about right. You good so far?
Yeah.
Now complete this into a parallelogram like that. Now the resultant vector is going to be starting at point A and ending in the corner of that parallelogram. So that red one would be the sum of vector AB plus CD. That's called the parallelogram method. Kind of fun, huh?
Yeah.
Now, new subtopic here, scalar. What did we say a scalar was, by the way? Scalar doesn't have direction. It just has magnitude. So it's just a number, a one-dimensional measurement of something, length, width, height, mass. So scalar multiplication of a vector affects the magnitude of the vector. Zoom in. So if I take a single vector and multiply it by a scalar, that changes the magnitude. What's magnitude again? What's magnitude of a vector? The length. The distance. So if I take a vector and multiply by a scalar, it changes the distance or the length of the vector. So, for example, let's do vector AB here. It's actually more common to name vectors using a single letter rather than the initial point and the terminal point. So, just to try to stay with what the book's going to do, they're going to call a vector a single letter like U or V or W or something. So let's call this vector U. Okay? If I want to now draw the vector 1/2 U, what do you think that's going to do? It's going to be half the length. What's going to stay the same though? The direction. So as best you can, it doesn't have to be perfect because we don't have compasses here or anything like that, but try to draw a vector in the same direction, but it's only half the length. Put her down. Make it okay? Names on them? Okay. Ooh, this can be tricky. Alright, same direction, half the magnitude. So that's how scalar multiplication works. Now, let's keep with this same vector for a moment. What would you think, just your first impulse, I want to know what your first impulse is if I ask you to draw this. Yep, opposite direction. Same magnitude, just in a different opposite direction. So try your best to draw that. Same magnitude, opposite direction.
Would the aim be what, too?
Yeah, if you wanted to still call it, yeah, the initial point would be point A. The terminal point would still be point B. So you aren't going to have to deal a lot with vectors in space like this. In space means it's not on a rectangular coordinate system. That's what it means to be in space. It's kind of hard to deal with. So you're going to most likely start just with vectors in the coordinate plane. Vectors in or on. I guess it's in the coordinate plane. It's much easier to describe magnitude, direction, location of vectors when it's on a rectangular coordinate system rather than out there in space, floating around.
I think just if we
So draw a coordinate system here, an xy axis. Now let's draw vector v right here. V can be represented as an ordered pair. So go back to vector v. Do this with a dotted line. So draw a horizontal component and a vertical component like that. Call the horizontal component A, the vertical component, call it B. So the way that we can represent the location of a vector would look like this. V equals, now for some reason, I don't know why, just vector notation they chose to use instead of parentheses, these little, I don't know what you would call those, but that's what they are. So vector V could be represented like that, where A is the horizontal component, B is the vertical component. Now the tricky thing is, it's not real tricky, there's an easy way to get around this, but that's not what I wanted. That's what nope. Alright. Just look up here for a second, don't try to draw this on your paper. What if I drew vector here, like that? Would it have the same vertical and horizontal component? Same vertical, horizontal. What if I drew it down here like this? Same vertical, same horizontal. So rather than thinking, all right, there's an infinite possibility of vectors that could be around the plane, a vector in standard position is what we want. What we really need to have is a vector in standard position. That means the initial point is at the origin or on the origin. So even though all of these vectors really are the same vector because they have the same horizontal and vertical component, what we need to do is write all of these vectors in standard position. So on the vector that you have already drawn, this one that I'm circling, let's say that we go over 2 and up 3. So mark that on your axis. We go over to the right 2 and up 3. And if you didn't really draw it that way, just fudge it a little bit so we can all have the same thing. Let's say that we go to the right 2 and up 3. Then that means the initial point of this is the point 2, 3. Let's say that the terminal point is, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So let's say the terminal point is a point 5, 7. All right, think about it for a second. Think about it for just a second. If I took this vector right here, this one that I'm circling, if I dragged this vector so that its initial point was at the origin, but it kept the same magnitude, same direction, how would that affect the terminal point? If I took this vector v and drug it down here so that the initial point is on the origin, how would that affect the terminal point? -2 from, which one was that? -2 from 5, because we have to go in this direction, okay? And -3 from the 7. Okay? So v is going to equal, if vector v was drugged down here, if we took 2 away from 5, then that's going to be 3. Wouldn't that be the horizontal component? And instead of 7, we've got a -3 from that because we have to drag this whole vector down 3 units. So what happens to the vertical component? It becomes 4. That's how you would describe vector v. These are called the components. Components of vector v. You can only call them components if the initial point is on the origin. Okay? So here's a quick example. Let's just blast through this one example here. Find the components. And this could be done without drawing it, but it might help to draw it, just to visualize where this is. But find the components of vector u with an initial point 2, -5 and terminal point 3, 7. So what this is a vector that's just somewhere on the coordinate plane. You've got to drag that vector so the initial point is at the origin so you can find the components of it. It could be done without drawing it. It might help to draw it though. Well, what do we think? What has to happen so that this initial point is all the way up here at the origin? It's pretty easy. We've got to move it up 5 first of all, so that's going to affect the 3 or the 7. That's going to make it 12. The vertical component becomes 12. And then we're going to have to drag this not only up 5, but then to the left 2. So subtract 2, yeah, subtract 2 from that 3, and that becomes 1. You don't have to do this, but, you know, if you're curious, you can now, this would be the terminal point of a vector whose initial point is at the origin. So if you go over 1 and up 12, shouldn't we have a vector that's the same magnitude, same direction? It's just in standard form. So let's see if that's the, oh, hey, pretty close. Close enough. Okay. Let's talk about how to find the magnitude. That's pretty dang easy. Magnitude of a vector in standard position. That's important. It's in standard position. You guys can probably figure this out. Take a look here at the screen. If I'm talking about this red vector that's in standard position, whose initial point is at the origin, how do you think we're going to find the length of that? Yeah, all it is Pythagorean theorem. And the reason it needs to be in standard position is if it's in standard position, we have the components, correct? The components describe the vertical component and a horizontal component. That's your a and your b value in a squared plus b squared equals c squared. So the magnitude of vector v whose components are a comma b is the square root of a squared plus b squared. What is this very, very, very similar to that we just barely finished talking about in chapter 8? It's okay if you don't remember the names of it, but that CIS business, you remember what I'm talking about? Writing a trig number in polar form, a complex number in polar form. Didn't we have to find that R value? Isn't this exactly how we did that? Vectors are very, very much related to complex numbers in trig form or in polar form, because you remember with that we had to find the distance and we had to find the angle. It's the same thing we're going to do here. We have to find not only the magnitude of a vector, but the angle that that vector makes with this horizontal axis here. Exactly the same thing as writing a trig number or a complex number in trig or polar form. But let's start with this, magnitude of a vector. Let's do some quick example. To find the magnitude, this is just a quick practice of using Pythagorean theorem, really. Part A, let's say the vector u is equal to 2, negative 3. Find the magnitude. Oh, the notation, by the way, I did mention this briefly last time, but the notation for magnitude is this. So the magnitude of u is equal to the square root of 2 squared plus negative 3 squared. Square root of 13. Not too difficult. Any questions on finding the magnitude of a vector? It's pretty easy. As long as it's in standard form. You gotta make sure that vector is in standard form. Or standard position. So, algebraic operations. We talked about how to add vectors geometrically by moving them around into the parallelogram or a triangle. But that's only if they're floating around in space. If they're on a coordinate system, we can add them algebraically. So these are algebraic operations of vectors. Rather than having to draw pictures, we can find a resultant vector by adding or subtracting components. Pretty easy. So if vector u has the components a, b, and vector v has the components, let's call them c, d, then you guys tell me, what if I wrote this, u plus v? What do you guys think we're going to have to do here?
If I advertise on your door here?
No, go ahead. Do I get royalties? What is that for?
For Math Club Target. Anybody's been involved with Math Club or been to competitions or thought about it but haven't come? You can still redeem yourself. Come to our Math Club Target.
Next Tuesday, is that what it says?
Next Tuesday. Yes.
Next Tuesday. Cool. Thanks, Troy. For those that haven't heard, we had a really good math club this year. They won a lot of competitions. Real good math club. Looks really good on resumes, by the way, for scholarships, getting into colleges, Sterling Scholar stuff. Okay, you guys need to get over your pride and stigma. Oh, math club. Okay, that's just a pride issue that you guys have. It's a lot of fun. They do some really interesting problems.
Haley Ford actually into it. But then I had fun.
Yeah. Anyway, let's get back to this. How do you add two vectors, do you think, if the vectors are in standard position? Say that louder. Oh, add the magnitudes? That's not a bad idea. It's not quite like that. It's not a bad idea. Real good thought. Other thoughts?
Add the components and then take the magnitude of that.
Okay. What were you going to say? Yeah. All you do is add the components. So the u plus w is going to be, it's going to have a horizontal component of a plus c. And it's going to have a vertical component of b plus d. To add two vectors algebraically, all I have to do is add their components. It's pretty easy. And the same would have gone for subtraction. Scalar multiplication. So if I had a scalar, let's say that k, and I wanted to multiply that by u, how do you think scalar multiplication is going to work? So k is a scalar. What is a scalar again? Just to remind everybody. A scalar is just a number. A scalar is it's just a number. So if I take a number and multiply it by a vector, we saw what that did to its magnitude. It increased the magnitude. Where was that one? In your notes, right here. If we took a scalar and multiplied by a vector, geometrically that increases or decreases the magnitude. But algebraically, what do you think that does to the components? What are some thoughts on that? Just multiplies the components, yeah. So the original components of vector u were a comma b. So k times u is going to be ka comma kb. That's how scalar multiplication works algebraically. But just keep in mind, geometrically, a scalar increases or decreases the magnitude of a vector. What are some other things here? Let's try a quick example. Example 3. Let's say that u is equal to 2 comma negative 4v is equal to negative 1 comma 2. Find 2u plus 3v. 2u plus 3v. Let's start with the scalar part, the 2u and the 3v. To u, that just means the components of u are increased by a factor of 2. So that's going to become 4 comma negative 8. And then 3v, the components of vector v increased by a factor of 3. So negative 3 comma 6. So that's the scalar multiplication part of it. Now, how do we add these again? Yeah, just add the 2 horizontal components together and then add the 2 vertical components together. So 2u plus 3v is going to give you the vector. What's it going to give you? 1 comma negative 2. It's so much nicer to add and subtract and multiply scalars algebraically rather than geometrically. How we doing? We've talked about how to find the magnitude. What haven't we talked about how to find? Remember, a vector is described using 2 quantities, direction and magnitude. We haven't learned how to find the direction. All right, think back to the last chapter. We just finished chapter 8. You remember those complex numbers on the plane? We had to describe their position in polar form using a distance and what else? And an angle. How did we find that angle? Tangent. Is this coming back to you?
Yes.
We better do it. Here's what I'm talking about. Let's say we had this complex number here. I don't know. Let's call this negative 5 plus 3i. We had to describe this in polar form using this value r and this value here theta, so that z was equal to r cis theta. This ringing a bell? How did we find this theta value? Theta was equal to the inverse tangent of b over a, right? So it'd be negative 3/5. Did that always give you the right answer the first time you did that? This inverse tangent will only give you angles in the first or the fourth quadrant, only. Inverse tangent on a calculator only gives you angles in the first or fourth quadrant. So you would have to use whatever angle this gave you as a reference angle if it happened to be in the second or the third quadrant. It's the same thing when we're trying to find the direction of a vector. So let's do direction of a vector. So here's a vector. Let's say vector v is equal to, let's do negative 3 comma negative 5. Two parts. I want you to find the magnitude again, just for practice. But then I want you to find the direction. The direction is described as a positive angle measure from the x-axis. So starting at the x-axis, the direction then would be the angle from the x-axis in the positive direction. to wherever that vector is. And it's the same thing that we did by describing the angle of those complex numbers. So 9 plus 25, square root of 34, that's the magnitude. If it simplifies, then simplify it. 34 doesn't simplify, but if it was square root of 36 or square root of 45, anything that could simplify, you'd be expected to simplify. And this is okay to leave it like that. The direction, though. Now, you don't have to do this, but just so we can have a visual here, you can draw this vector. We have this vector right here. We already found the magnitude to be square root of 34. The direction would be this angle. Whatever the measure of that angle is, that would be considered its direction. So what are we thinking? Help me out here. Okay, inverse tangent of b over a. Okay, so that's going to be the inverse tangent of 5/3. That's a calculator problem. That has to be done on a calculator. So the inverse tangent of 5/3 is what? That's 59 degrees exactly. That is an angle in the first quadrant. Okay? Where our vector is pointing down into the third quadrant. So that means 59 degrees is a reference angle. You have to add that to 180. Exactly. So 59 degrees plus 180 is what? 200 and... So that would be the direction then of the vector. Almost exactly the same thing that we did in chapter 8 with polar form of complex numbers. There it is. Okay. Let's talk about what's called a unit vector. A unit vector is any vector whose magnitude is 1. Any vector whose magnitude is 1 is called a unit vector. It doesn't matter what the direction is. It could be pointing anywhere. As long as its magnitude is 1, it's called a unit vector. So there's an infinite number of unit vectors possible depending on where the direction is. But 2 in particular are very, very special. 2 unit vectors in particular. One is called I, vector I. Super special. The components of vector I are 1, 0. So where does that mean it is? Where is vector I? Not necessarily in quadrant 1, because you go over 1 and up 0. It's just right on this. So it's in between quadrants 1 and 4. It's right on the x-axis. So that one's a special little guy. The other one is vector J. whose components are 0, 1, equally as special, just different. That places vector j on the y-axis, correct? Now, I need you to do your best to draw this as accurately as possible and make it a little bit larger so that your accuracy can be better. So draw a big old graph like this. And try to space these out evenly. So let's go 3 on the x-axis, and using the same distances, let's go 4 on the y-axis. Now get out your colored pencils. Oh, you don't have any? Oh, do you? If you want, it might make this easier. I'm going to use a different color here. This vector right here, which one is that? That's I, okay? So put vector I on there. This vector here, that's vector j. Now this is going to be a little bit of the algebraic addition of vectors and also the geometric addition of vectors that we talked about right at the beginning. If I asked you guys to draw me this vector, 3i plus 4j, 3i plus 4j. Let's do this geometrically first of all. Geometrically. What is 3i? What does that mean? What does a scalar do to a vector? Do you remember what a scalar does to a vector? It increases the magnitude. So if this is I, then wouldn't 3i just be twice or 3 times the distance? So this right here would be 3i. You guys follow?
Yeah.
Now, similarly, 4j would just be a vector in the same direction as j, just 4 times as long. So now do that. So now we have 4j. Oh, these distances aren't the same. My scale's a bit off. Anyway, that's all right. I know, it looks kind of like the same. It shouldn't be. Do you remember, look at the beginning part of your notes. Take a look at the parallelogram method that I showed you. Take a look at right at the beginning of your notes. How do you add 2 vectors using the parallelogram method? So I'd have to draw a line here. I'd have to draw a line here to make a parallelogram, right? And then where would the resultant vector be?
The diagonal one.
The diagonal one, yeah. The length of it? Yeah, the magnitude of it would be the square root of 3 squared plus 4 squared, yeah. Now, this vector right here, would you guys agree with me? Let's give it a name. Let's call this vector v. Would you guys agree with me that vector v could be written this way? Yes or no? What do you think? Could vector v be written that way? 3, 4? Don't you go over 3 and up 4? To find a terminal point? Would you also agree that vector v could be written this way? Isn't that how we got vector v in the first place? Isn't that where vector v came from? So the whole point of this is that these are equivalent notations for the same vector. Okay? This is called component form because this describes the component. Okay? This is a vector in terms of I and j. They are the exact same thing. There is no difference. And when you guys, or if you guys ever take a physics course or an advanced physics course involving calculus, vectors are written in this form, the ij form, rather than in component form. They mean the same thing. Okay? So, just to do a quick, it's going to seem easy, but just so I can be sure you guys understand what I'm talking about. Example 5, or 4, what are we on? 4. Example 4, write vector u in terms of I and j. So if vector u, it's going to seem easy, but let's just make sure we understand this. If vector u is equal to 5 comma negative 8, then taking a look at what we just did, what would this vector look like in terms of I and 5i minus 8j, exactly. So vector u could also be written as 5i minus 8j. So, I mean, it's pretty easy to do. How would you, is there any difference, what do you guys think? Is there any difference in finding the magnitude if it's in component form or in terms of I and j? Is there any difference in finding the magnitude, the distance? What do you think? How do you find the magnitude when it's in this form? Square root of a squared plus b squared. What do you think here? Same thing. Square root of a squared plus b squared. How would you find the direction? Same way. There is absolutely virtually no difference in how these, I mean, they look different. That's the only difference, really. But how you work with them is exactly the same. If I had two vectors in terms of I and j, to add them together, you would add the I parts, you would add the j parts. It's exactly the same thing. But the reason in physics that this is more useful is in physics you have to break down vectors into horizontal and vertical components and then shrink them down into unit vectors a lot of the time. So, anyway. We're just about done with this section. We're almost ready to wrap it up. Horizontal and vertical components of a vector. Let V be a vector with magnitude and direction theta so let's draw this real quick. So the length of this vector I'm calling the magnitude of V. The direction, let's call it theta. Now rather than just telling you the formula, you guys are usually pretty good at coming up with these on your own. What we're getting at is how could we describe the horizontal and vertical components of a vector if all we know is the magnitude and direction. If we didn't know we didn't know anything else. So how would we find this length here, for example, or how would we find this length there, for example? Think about it for a moment. Hold on for just a second. I want to give everybody a chance to think, and then I'll ask you here. So let's assume we don't know the components. All we know is the magnitude and the direction. That's all we know. But we don't know, like, the A and the B value. That's what we're actually trying to find. We're trying to find the A and the B value. So think about it. 15 seconds. We've done stuff like this before, back in our beginning part of trigonometry. Who wants to explain it? You want to give her a go?
Sure.
Mr. Push-Up? That's going to be your name from now on. Just,
For the next
The
week.
remaining 4 times we see it.
yeah. I wish we'd known this earlier. Anyway,
He's so strong.
I think you should arm wrestle.
Okay. So, well, it'd be like sine theta would be opposite over hypotenuse, and hypotenuse would be the magnitude of the vector. So then you'd have sine theta equals, let's just call it A over B. And then if you times B by both sides, you get A alone, so then it would be sine theta times B, or B times sine theta equals A.
exactly.
And then B would just be B times cosine theta.
Exactly. Exactly. That's a good explanation. This is all right triangle stuff, you guys. This is all right triangle trigonometry. If we wanted to call this component A, for example, the horizontal component is always called A. Isn't this the adjacent side to that angle? And we know the hypotenuse. So we could say, this is what Braden was explaining, the cosine of that angle theta is equal to A divided by the magnitude of V, correct? So just multiply both sides by the magnitude of V, and what we end up with for a horizontal component is A is equal to the magnitude multiplied by the cosine of the direction, cosine theta. Similarly for B, the vertical component, that's the opposite side from the angle theta. So which trig function we use in here? The sine. So B can be found by saying, all right, the sine of theta is equal to B over the magnitude of V. Multiply both sides by the magnitude, and you end up with the equation B is equal to magnitude multiplied by the sine of theta. So example 5. Given the magnitude is equal to 8 and direction is pi thirds, write V in terms of I and J. So find the horizontal vertical components and then write vector V in terms of I and J. Well, what are we thinking? We need to find A and B. Should be fairly easy problem. According to the formula here, A is equal to the magnitude V multiplied by the cosine of the direction. And nice for us, they gave us a pretty easy angle to work with. Pi thirds, that's just on your unit circle, pi thirds. Cosine of pi thirds. I can't understand when you're all talking at once like that. It's really hard. What's the cosine of pi thirds? 1/2? So it looks like the horizontal component is 4. The vertical component is found using this formula. Magnitude multiplied by the sine of pi thirds. Sine of pi thirds is what? Square root of 3 over 2? So that's 4 square roots of 3. So then in terms of I and j, vector v is going to be what? 4i plus 4 squared to 3j. Being able to do this is more important than you think in terms of practicality of this. Who's taken physics? Raise your hand if you are in physics or have taken it. You guys learn about forces? Do you guys learn about forces in physics? What's a force? How do you describe a force? In physics, I don't know. It's been a long time since I've taken physics. But is it described using a scalar quantity or a vector quantity? Do you understand the difference between the two? A scalar quantity is one-dimensional. Is that how you describe a force? You guys that are in physics, help us out here. I know you have a good physics teacher. He had to have taught you this.
Generally, we keep it to the xy directions.
But doesn't a force have to have direction and magnitude? It's a vector. If a force is described as a vector quantity, so when you're given a force, you're given its magnitude and direction. So if multiple forces are acting on an object, you've got to be able to break it down into component form like this to either add, subtract, whatever it is. So here's a application example of how you would use this. All right, draw this picture here. We have point P sitting about right here. We have a force acting on point P that we're going to call F1. We have a second force acting on point P. Ooh, let's try that again. Straight line. Let's call that F2. So we have two forces acting on point P that are moving away from point P. So it's going to move point P. What we have to figure out is how does it move it? Now geometrically we could figure this out by using the parallelogram method to find the resultant vector. What we're trying to find is the resultant vector. It's going to kind of be pointing up in this direction, right? If we did the parallelogram method. But we're not going to do that. We've got to do this algebraically. So what we have to do is find the resultant vector using algebra. This is all we know about the forces. Force 1, okay? Let's say force 1 has a magnitude of 10 pounds. Okay. The direction, I want you to do this. Draw a dotted horizontal line right through point P. Put an angle from that dotted line to force 1. Let's call that 45 degrees. Okay. Do the same thing from the dotted line all the way to force 2. Let's call that 150 degrees. Okay, force 2 has magnitude 20. Your task is to find the resultant vector. I've used this word before. The resultant vector is the result of adding two vectors together. So if we added force 1 vector to force 2 vector, the resultant vector would be the sum of those two vectors. This has to be done algebraically, not geometrically. What that means is if point P is acted upon by these two forces, what happens to point P? Where does it go? It moves, but in which direction and how far does it move if it's acted upon by these two forces? So we need to do exactly what we just did. If we can take each force and write them in this form right here, How would that help? Why would that help?
You can add the vector.
Then we could add the two vectors. Easily add the two vectors. If they're in this form right here, you guys, how do we add the vectors if they're in this form? How do we add the vectors?
Add the I.
Add the i's together, add the j's together. So as long as we can write these two vectors in component form or in ij form, it doesn't really matter which one, then we could find the resultant vector simply by adding the similar components together. So that's your task. For F1, we have to do the same thing for F2. Yeah.
How we done did?
There were some strange numbers, but let's see, what was the magnitude? So this is going to be, for A, this is going to be 10 times the cosine of the angle. B is going to be 10 times the sine. 45 degrees, that's not too bad. What's the sine of 45 and the cosine of 45? They're both the same.
4, and then 20.
Well, 45 is pi over 4, you're right, but the cosine of that is square root 2 over 2. So this is 10 root 2 over 2. This is also 10 root 2 over 2. So both of those are 5 root 2. So for force 1, that could be described as 5 root 2i plus 5 root 2j. So that's force 1. Force 2, same thing, just different numbers. A is equal to, what was the magnitude? 20? 20 cosine of 150. B is equal to 20 sine of 150. All right, help me out. I don't have my unit circle in front of me, but what's the cosine of 150?
5 pi over 6.
Well, the 150 is 5 pi over 6 in radian form, but then you take the cosine of that. Negative root 3 over 2? Okay. Here's what I'm talking about, Nick.
No, I get it. Don't worry.
You got it?
Yeah.
I just got to double check you guys anyway. Not that I don't believe you, but I don't believe you. I do believe you. The cosine of 150 is negative root 3 over 2.
Yeah.
You guys are right. So this becomes 20 times negative root 3 over 2. And then the sine looks like it's going to be 1/2. Well, that's a nice number. Okay, that one gave us a nice number. Half of 20 is 10. This one's not so nice. Negative 10 root 3. So force 2 can be described as negative 10 root 3i plus 10j. So, I know this is going to look funny, but the resultant vector, now that we've written our vectors in terms of I and j, what's the resultant vector going to look like? We add the two horizontal components. Can we add these together? Not, I mean we can, but the way that we write it, we can't write that as one term. This is what it's got to look like. It's got to be 5 root 2 plus negative 10 root 3i. That's the horizontal component. Where did this come from, in case we're wondering? Where did this come from? Adding the two horizontal components here. Now the vertical component, so that's plus. Now we do the same thing. Since they're kind of funky numbers, it's 5 root 2 plus 10, and that's going to be the j, or the vertical component. So just to remind you, what we could do geometrically to add these two forces together is the parallelogram method. So if we formed a parallelogram, ooh man, hold on now. There we go. If we formed a parallelogram, then this is exactly what we just found, that vector right there. The problem is, geometrically, we don't know the components. We don't know the I and the j, so we had to make this into an algebraic problem. But this vector right here is exactly what we just found right here, just using different methods. Yeah?
Does that mean, like application, like speaking, if somebody pushed at a 45-degree angle 10 pounds and somebody else pushed 20 pounds at a 150-degree angle, then it would change the direction to whatever angle that is?
Yep. Did you guys all hear what happened? He's absolutely right. Let's say the point P is just some object. Okay? It gets hit in this direction with a force of 10 pounds, but then it gets hit in this direction with a force of 20 pounds. Now this is called Newtonian Physics, where you don't take into account air resistance and friction and all that kind of stuff. So disregarding all of that, what would happen to point P if it's acted upon with a 10-pound force this way and a 20-pound force this way? Well, point P would travel in this direction up to here. Does that make sense? What's that? No. That would be cool though, wouldn't it? Wouldn't it? But no. So in college, you guys, general physics, the very first physics course that you take, is a lot of this stuff. You have like a car wreck. Let's say that this is a car. It gets hit by two cars from different directions. What happens to the car as it skids? And then you have to take into account friction, and you learn how to do that. But it's kind of cool stuff. Or in space, where you don't have any friction or gravity or anything like that, what would happen? It's just it's a lot of cool stuff. So that's